Okay, welcome back for this second video where I discuss an engineering optimization problem and discuss some of the decisions that you go through when you define an optimization problem and how you can use your engineering knowledge to make these decisions. I left you with the question, what is a practical consideration when you decide on the number of design variables to use in your optimization? Well, if your answer was, the more the better, in theory, you are correct. But my question was, what are the practical considerations? And here are some of the ones that I have encountered, not just in this problem, but also in other optimization problems that I've run, optimizing composites, optimizing shapes of airplanes, etc. That in general, you want to have enough freedom, so enough variables, to effectively change your structure or your shape or whatever you're optimizing, right? In this case, I want to effectively change the stiffness and affect my load paths. But not too many. And I'll come back to why not too many. In general, you have constraints. And even though you might be able to have infinite wiggles in your path, this limitation on steering radius will really just take a lot of that freedom away. So you kind of want to have slightly more freedom than your constraints might allow you, but not much more because it's not really going to help you. The disadvantage of having too many variables is that it might be making your optimization hard to converge. You might be able to end up in a local optimum. You might have a lot of, again, infeasible design space where your optimizer might be doing evaluations in areas where you will never find an optimum. And so it's kind of a fine balance, and sometimes it takes some trial and error to kind of understand what is enough and what is too much. And then there are some tricks where, again, you use your engineering knowledge to try to keep the number of variables down. For example, you can make use of symmetries, and I will use the last two questions that I had as illustrations of where you might be able to use symmetries in this particular setup. So remember in the requirements, I talked about symmetric loading. If you have this cylinder and you're loading it in bending, and you would look at the cross-section of that cylinder, the left and the right-hand side of the vertical plane see identical loading. So when you run an optimization and you would define the left and the right independent of each other, what I would expect the optimizer to come up with is kind of structurally the same behavior on the left as on the right. But why would you let the optimizer try to figure that out if you already know that as the engineer? So what I did here was on the left-hand side and on the right-hand side, I defined the same fiber orientation to get the same stiffness out. And so that's why you see T1, both sides of the symmetry plane, T2 on both sides of the symmetry plane, etc. And so that kind of saves you 4 out of 5, or sorry, 3 out of 8 independent variables. So you only have 5 variables instead of 8. Now you do see that going from the top to the bottom, the variables are allowed to be different. And that's because we have tension on the top, so where the T0 would be, and compression on the bottom. And so I figured, we probably want to have the, enough variation to have different structural behavior on the top and on the bottom. And what I found that indeed the curvature or the radius of curvature was pretty restrictive. So when I went beyond the 5 variables, note I start with 0 and end with 4, that it didn't really give me any more freedom to change more rapidly. So that's how I ended up with 5 variables per layer. Now, another form of symmetry is kind of through the thickness. So if we now look at the number of layers stacked on top of each other, there's a concept that we use that's called the symmetry plane. And that symmetry plane is exactly what the name suggests. There's symmetry above and below this plane in terms of the definition of each layer. Namely, at the same distance from the symmetry plane, you're going to have the same layer. And the reason for that is if you take a flat sheet and you don't apply this symmetry and you cure it, kind of bake this composite in the oven or in the autoclave, it will come out as a potato chip. So you want your structure to be flat, and so you don't want it to be a potato chip. And this is something that people who've taken a class on fiber reinforced composites should be familiar with. It's symmetry. So now if you started with 24 layers and the top half and the bottom half need to be mirrored, you end up with only 12 layers. In addition, there's a concept that is called balance, and it kind of is somewhat similar, but it is with respect to your reference direction. And that says that for every plus ply, you might want to have a minus ply, and that's to avoid some structural coupling effects that take place if you don't do that. There are other ways to achieve it, but those are way more complex, so it's much easier to just apply these engineering rules. And now you've gone from your total number of layers divided by 2 to your total number of layers divided by 4 in terms of how many independent ply definitions you can have. So these are two examples using your engineering knowledge to apply symmetries and reduce the number of unnecessary variables. I'm not going to say that the things on the right would have automatically fallen out, and I meant the symmetry for manufacturability, would have automatically fallen out if you hadn't defined them, because those are really more constraints coming from real life rather than that the optimizer would be able to infer it from the analysis. Now we're going to change topics a little bit by going to a change of variables. There are multiple reasons why you might want to apply a change of variables, either to the actual variables or to your constraints. And so I picked an example here where we're looking at this steering constraint. And I've mentioned it a couple of times, and now I'm going to put a number on it. Let's say the steering radius has to be larger than 20 inches. Now, if you look at the mathematical formulation of your optimization problem, my question is, which of these formulations is better? Are you going to say your radius has to be larger than 20 inches? Or, knowing that radius and curvature are the inverse of each other, we're going to say that curvature has to be, between 1/20 and minus 1/20. Or do you say it doesn't matter? Now, assuming that you made up your mind, keep in mind remember what you picked. I'm going to give you a hint. What if I told you that curvature can go to 0? Does that change your answer? Okay, so you're probably thinking, okay, so what? If curvature goes to 0, radius goes to infinity. Infinity is bigger than 20, no problem. Well, as engineers, that concept is very easy to grasp. But if you tell that to a computer, the computer will derive the curvature from the path definition. And after you calculate the curvature, it will calculate the radius. Which means that if you are trying to divide by 0, your code will crash. Because optimizers typically don't know what to do with inf. You can have Python maybe print, it's going to be inf, but the optimizers still don't know what to do with that. Whereas if your curvature goes to 0, there's no problem. It's 0, it's between these two values, and the optimizer will happily continue. Well, this is one that you would probably discover pretty quickly once you start running the optimization. Because if two of the, the design points have the same fiber angle, you're going to have a straight line and your curvature is 0 and your analysis crashes. So you change it. Now, on top of this choice, I actually applied another change of variables to the same constraint. What I noticed was that when these curvature values get really, really small, the sensitivities also become very small. And you can normalize them. You can say, okay, well, I'm going to take curvature divided by 0.05 has to be smaller than -1 and +1, for example. That only kind of shifts the problem in terms of the curvature, because it can still get to really, really small values. And if you take the log of the curvature, the closer those values get to 0, kind of the bigger the negative numbers become. And the optimizer just responded much better to that, because the sensitivities were no longer kind of in the noise of the optimization. Now, that one was not necessarily a straightforward one. It took some time to figure it out. But that's one example of using a change of variables to help your optimizer converge better. Now, I want to give one more illustration of a change of variables that might help your optimization. It's not related to the problem we've been discussing, so it's a little bit of a side discussion, but it's a kind of challenge we run into almost every single time I set up an optimization problem. And I'm going to use an example where in aircraft structures, quite often we have a skin, and this is going to be a cross-sectional view. And on that skin, we have stiffeners. There's one, and there's another one. The variables that you might want to vary might be the spacing between these stiffening elements. I'm going to call that S. And the width of the flanges of these stiffeners. And for simplicity, I'm just going to assume that these two are going to be similar. Now, in your optimization, if these are your variables, you might want to say, okay, I want my width to be between, I'm going to say 1 and 4. And, that's just an arbitrary choice. And the spacing can be between 3 and 8. Now, when you start an optimization, depending on how you apply it, you might have a design of experiments where you just kind of look at arbitrary combinations of your spacing and your width and try to evaluate whatever it is that you're evaluating. Might be weight, might be strength, might be buckling load, whatever it is. But because they can be kind of in arbitrary combinations, you might end up with your width being 4 and your spacing being 3. Well, what happens when that's the case? Well, you will have one here, and you'll have the other one here, and they overlap. And then you have your skin. Well, again, depending on how your algorithm is set up, it might crash because this is overlapping, or it might give you an answer which is almost worse because it's going to give you a nonsensical answer. And so what you might want to do is you might want to apply a change of variables. And actually, before I go there, you might say, well, what if during my optimization, I'm going to say this gap, this one doesn't work very well. This gap has to be bigger than, I'm going to say 0, it could be bigger than a value. So you can say, well, I want my gap to be bigger than 0. Well, during your optimization, you might not always be evaluating points that are feasible, which means it can violate this constraint. So what you could do instead, you could say, okay, well, I'm still going to define my width of the stringer flanges to be between 1 and 4, and I'm going to say my gap has to be between 0 and, let's say, if this is 1, I still want to be able to get to total spacing of 8. So I'm going to say it's going to be between 0 and 6. Now, note that we actually made the design space bigger now, right, than it initially was, because if the width is 4, then you're going to have a total spacing of 10. Well, in that case, you might want to set a constraint that your spacing has to be smaller or equal to 8, and maybe your spacing has to be bigger, equal to 3. Which means that you still might be evaluating points that are outside of this range, but it's not going to make your optimizer crash. So when you start defining your problem, you might want to think about, okay, which kind of combinations might actually violate this constraint. Now, if initially you said, oh, my spacing always has to be between 5 and 8, then you don't have to bother. But if in the future there might be a possibility that this number gets smaller than 2 times this width times a half, so then you might want to define it as a gap in addition to the width. So this is, again, a kind of a geometric consideration that you might encounter quite a bit when you're doing either shape optimization or structural optimization with different number of elements, spacings, maybe cutouts, those kinds of things.